Well, last time we kind of left on a kind of weird note where I couldn't remember whether it was cosine theta or sine theta. So let's start from there. We're going to look at what's called the dot product. Right, so essentially the dot product is a calculation that you do on either 2 or 3-dimensional vectors. Let's do the 3-dimensional vector of the formula, but you can certainly adapt it into a 2-dimensional formula. Oh, there we go. So I've got my 2 vectors, which I'm calling u and v. And if you can imagine that this vector is u, and this one over here is v, and we're trying to, or we'd like to know this angle between the 2 vectors, then the dot product, which is essentially called u dot v, and it's equal to the product of the x, y, and z components added together. Then the cosine of theta is this fella divided by that guy. So you could, I guess you could abbreviate that or change that and say that theta is the inverse cosine of this. Typically I do that and then I do an inverse cos at the end. Angles for theta are either radians or degrees. It depends on the context of the question. If the angle happens to be an exact value, you know, like it's a 30 degree or a 45 degree or something like that, then they may well ask you to give the answer in radians. But typically these 2 vectors, the angle between them is just random digits. So you're more likely to do 14.1 degrees or something. So let's do an example. Suppose I have a vector u and it's 1, 2, -3, and I have a vector v and it's 5, 2, 1. And the question was simply, what is the angle between these 2 vectors? So can you imagine that these 2 vectors are in 3 dimensions, so they're kind of sticking out of the wall, you know, sticking out like this. And if you orientate it, you might be able to see what the angle looks like. You're trying to find this angle here. It's going to be something between 0 and 180. Let's find out what we get this time. Well, if I take the dot product, it's essentially 1 times 5, 2 times 2, and -3 times 1. And that guy is 5, that guy is 4, and that guy is -3. And I hope that ends up being 6. I also need to find the length of these 2 vectors, their magnitude as it's called, because they're going to go here and here. And for the first one, its magnitude is the square root of 1 squared, 2 squared, and -3 squared. What's that? 1 plus 4 plus 9. So that's the square root of 14. And the second one is this guy here. And that's going to be 5 squared. Oops, done the answer there. 2 squared, 1 squared. What's that? 25, 35, 41, 42. And you put the package together. The cosine of the angle between those 2 vectors is the dot product divided by the 2 magnitudes multiplied. And the dot product is 6. And these 2 guys are the square root of 14 and the square root of 42. Now, normally when we do when we do magnitudes of vectors as we do here, we would write them down in their simplest form. I don't think in this case anything comes out, but can you imagine sometimes this might be the square root of 20 and this might be square root of 50 or something. Normally you would rewrite those in their standardized form. Typically, unless the question asks for these things, you can leave them in the ugliest form you like, because they're just going to end up in the calculator anyway. So there's not a lot of benefit to taking a really big fraction, a really big square root, a radical, and simplifying it, because you're not going to do anything with it. So I'm going to go into my calculator here, and I'm going to deliberately do a couple of mistakes. The first mistake I'm going to do, so I kind of won't be doing it at all, is that you might have your calculator in the wrong mode. Typically, these questions are always degrees, right? Unless they specifically say radians, assume everything is degrees. So first mistake I could do would be to not realize that and have my calculator in radians. Now, you'll normally know that it's radians when you keep on getting angles like 1.2 and 2.3, which are very, very small angles, right, in degrees. And the reason you're getting 1.2 or 2.3 is it's 1.2 radians or 2.3 radians. So it might seem like a trivial thing, but trust me, you'll do it if you're not careful. So just make sure calculator is in degrees, call it good. Now this is a different mistake. I'm going to calculate this guy. See if you can see what I did wrong. 6 divided by square root of 14 multiplied by square root of 42.
Just the order of operations, you're going to not divide by that 42 square root.
That's right. What the calculator is going to think I mean is 6 divided by square root of 42. That's cool. Then it thinks multiply the answer by the square root of that fella, right? So if I do it, you normally know that if you've done this mistake. A cosine equal to 10.39 is probably not a good idea. Right? It just looks wrong. And if you try an inverse cosine in that, you'll find out it says error. So let's fix it. So what you need to do is 6 divided by, put a bracket so that the two guys in the bottom get done first, essentially. And then you can do the square root of 14. Multiplied by the square root of 42. And we got a nice 2.4247. So 0.247. And then I'm just going to do an inverse cosine in that fella. Actually, if I leave it like that, you can just go inverse cosine and then use the answer button so it gets you the whole thing. And the answer is about 75.67 and so on. Another minor mistake is, look at the question. Does it want the answer to the nearest whole number? Does it want the answer to one decimal place? You might think that's not a biggie, but if it wants it to one decimal place and you do it to 2 or something different, it'll say you're wrong, even though you're not really that wrong. So let's assume that this one happened to be give the answer to one decimal place. And that's pretty much how you do a dot product. It's, in my opinion, it's very plug and chug, isn't it? You've got a formula. Each piece of that formula you can calculate. You put all the pieces together. You find out what the cosine of the angle is, and then inverse cos, you're done. Now, I believe there's one exception to the inverse cosine. Write this down. If they wanted to get the exact value, right? So if the phrase, I want the exact value for that angle, that's what you'd be writing down. Okay. Now, if they're not, which the vast majority are not asking you that, then you're going to do this fella here. So exact value means what it says. You do not round anything off. You do not calculate really anything. And the best you can do is tidy it up. In that case, this weird fella here might end up being simplifiable. I know this one isn't, but I could imagine a situation where at least one or both of these square roots could be turned into something a little bit better and maybe cancelling with that 6.
I have a question.
Yes.
My question's about the lines that they mean magnitude or absolute value, right?
Yes. Well, they're both the same thing, strangely enough. I'll try and explain what I'm getting at when I say that. The two vertical lines that are absolute value. There are some textbooks that do it as a double. Have you seen anything like that?
Yeah.
It's the same thing.
Okay,
Right.
because I was just confused why you were square rooting it once you have applied that it's like magnitude.
Well, the magnitude needs a square root because the magnitude is the length of something, and part of the formula for getting the length involves square rooting the x, y, and z components after they've been squared and added. If I went and said to you that the vector v was v1, v2, v3, and I asked you to calculate the magnitude of v, the formula for it has a square root in it. Right, so you need that square root if that's what you're asking.
Okay, yeah.
Right. Now, back to this notation here. It comes from this. We don't normally think of it this way, but you can actually think of a normal one-dimensional number, right, which is called a scalar. Now, if you had a scalar and it was 2, right, that just means a normal number to us. Then if you put a dot there on 2, if you draw from the 0 on a number line to 2, do you see that you get a little baby vector? Actually, they're all horizontal, aren't they? Because in a number line, that's the only direction you can go. Isn't the magnitude of that vector, so if I call this guy v, the magnitude of that vector, isn't it the absolute value of 2, which is 2? For instance, suppose I have a vector u, and I'm talking about u being this vector over here, going that way. Make that u. Wouldn't the magnitude of that vector be the absolute value of -1, which would be 1? So do you see how that absolute value notation, those two vertical lines that we're used to calling the absolute value, isn't that just a special case of the bigger picture of the magnitude of a vector? Now, if you do it in 2 dimensions, same thing, right? The magnitude of the vector just ends up being the length of the vector from here to here. And if you do it in 3 dimensions, the magnitude of the vector, same thing. You can then move on to 4 dimensions, but I'm not quite sure my brain can handle it. I'm not quite sure what the magnitude of a 4th dimensional vector is. I can't even imagine a 4th dimensional vector for any great detail. Okay, so far so good. Right, let's move on to some puzzles. Puzzles are fun. This is 2-dimensional vectors, so we're doing 2D, but it could work with 3D. Suppose I was asked in this question here, some colors in here. This is vector u. This is vector v. We're being asked to find the dot product. Now, if you rearrange this version of the dot product, can you see with a little cross multiply that the dot product is equal to the magnitude of u times the magnitude of v times the cosine of the angle in between? You agree that's just a rearrangement of the dot product. And so the question was, find the value of this dot product from this picture. Well, there's not an awful lot going on here numerically. We're being told that all the sides are the same length, and I'm calling that length C. And this angle here will be theta. So let's put together the package. Won't the length of vector u be c? The length of vector v will be c, followed by the cosine of something. Is there anything you can tell me about the value of theta here?
It's an equilateral triangle, so it should be cosine of 60 degrees.
Agreed? You see that? So what might have seemed like not an awful lot of information actually is c times c is c squared. Right, and cosine is 60. Unit circle, go to 60, find the x coordinate of it. Oh, no one remembers.
Would it be square root of 2 over 2?
That would be for the cosine of 45 degrees, but you're one of the three possible answers, but it wasn't that.
Is it 1/2?
Thank you. And I guess this is me just being a bit lazy, but there is your answer. Now, another puzzle. And I'm going to be using this in a few moments. Suppose the dot product is 0 and u and v, neither of those two vectors are the 0 vector. What is the geometric property or connection between those two vectors now? U dot v is 0. So what is the connection between the two?
That means that they have the same magnitude, but they're going in opposite directions so that they can't.
That would be if I said something like that. But this is the dot product is 0. So I'm not saying that u plus v equals 0 vector, which is kind of what you just said. I'm saying the dot product is the number 0.
So the cosine is 0.
Okay, which means what about the angle? You're right. What size is the angle? It's not a random number, it's always the same value.
Isn't it 90 degrees?
Yay, that's what I wanted to hear. God, it's like being at a dentist, I'm pulling teeth here, right? So, one of the properties of the dot product is that if the dot product is 0, you can immediately assume that the angle between the two vectors is a right angle. It's 90 degrees. So let me give you some names for these things. That is called a right angle. It's also, sometimes you say that the two vectors are perpendicular. And then there's a third, probably less known word. Orthogonal. You heard that term? So two things are orthogonal means that two things are perpendicular, which means two things are right angled. So if you see orthogonal, well, you just say it means this and it means that. So you don't think that there's something different going on. There is a very interesting reason why that term actually gets used now in advanced math rather than these two. If you think about two vectors who are at right angles, so here's two vectors at right angles, right? If I rotate them this way, you can see it better, right? But it doesn't matter how the orientation is, as long as you keep them fixed. They're always right angled, right? Fine. Get them like that. Now, you would say right angled, and you would say perpendicular. But what happens when you move beyond 3 dimensions? It doesn't really make sense to say that the angle between two fourth dimensional vectors is 90 degrees, because in the fourth dimensional world, what even does that look like? So the word orthogonal takes you away from the geometry and just says that these two vectors have a very special property. Their dot product is 0. And we'll leave it at that, and we won't try and visualize anything more than that. Let's try an example of calculating work. Now, the work done using a force here's the whole question. How do you calculate? Essentially, this question boils down to this. How do you calculate the work done in using a force F that's pulling in this direction on an object that's being moved from this point to that point? So I'm not great at this, but can you imagine this is P, there's Q, and that you're pulling this force kind of in this direction. Now, actually, the most efficient direction would be pulling along PQ, but you don't always get to do that. This would be the equivalent of, do you know the ones where you take a box and you pull it up a hill? They're like, for some reason, that seems to be a favourite question amongst the statics people. Who on earth wants to pull boxes up hills? But evidently they do. So the vector F is the red guy, and P to Q will eventually become a vector. So the formula for getting the work done is the dot product of F and the vector joining P to Q. So if you want to see give me an application of me actually just using the dot product, right? Then it would be this example here. So how would I go about making this happen? Well, I would need to find the vector joining P to Q. And I'll do my usual shortcut. Remember, we talk about second takeaway first. So 5 take away 1 gets you 4. 6 take away 3 gets you 3. -3 take away -2 gets you -1. So that's the quick way of finding a vector joining 2 points. Take the x coordinate of Q and subtract the x coordinate of P, right? Y coordinates, Z coordinates. What I call second takeaway first. Well, you go over here and you do 1, 3, -2, dot product with 4, 3, -1. And that gets me 1 times 4. Add 3 times 3. Add -2 times -1. And I'm looking at 4 add 9, I believe add 2. In this case, it looks like it's 15. I'm not a physics person or an engineer person. I think work done is the units. Newtons, or it's Newton meters, I think, isn't it? Newton meters.
I want to say joules, right?
Is a joule a Newton meter? Because it might be the same thing.
Yeah.
Okay, so we're go. Are we cool with that? Right. So what we're just looking at are some examples of the dot product being used. Over here, it's a totally algebraic situation. Find the dot product of a triangle where you're not told any numerical information, except indirectly, you know that 60 degrees. Find the work done in using this force, pulling something from there to there, which is a pretty common one. We're cool?
Mr. Robertson,
Yes,
I have a question.
go for it.
So in this context, the F vector represents the force, like moving an object from. Wait, but what does the vector PQ mean? So,
P and Q would be the, can you imagine there's a box here? And
Yes.
P to Q is the box being slid from here to here. So P to
Yes.
Q is the second vector. So P to Q would roughly be the hill that you're pulling this box up. So you've got a hill.
and what about F? What does that mean in this
right, well,
context?
If you can imagine there's a hill here and there's a box on this hill and you are pulling this box, but you're not pulling the box in the same direction as the hill's going. You're pulling it slightly off. You're pulling to this. So F is the representation of the force and the direction of that force that you're pulling this box up a hill. Can you imagine we're dragging someone up a hill, but you weren't dragging it in the angle that the hill was, you were dragging an angle, say, of 45 degrees. That would be your F. It would be the angle that you're pulling this box. So I can imagine a rope attached to this box and I'm pulling it. Now,
Thank you for the clarification.
okay. By the way, if you find just the magnitude of F, right? So the vector F is this guy here. If you find the magnitude of it, isn't that actually the units of force that that particular vector is pulling in? You know, if I doubled these numbers, wouldn't I be doubling the force I would be using in pulling that? Instead of giving it a little gentle tug, I could be giving it a real heavy tug. So the length of a vector very often measures the force that's being used. The vector itself isn't just that, it's the force and the angled orientation that you're using as well. You know, pulling something vertically upwards is not the same as pulling something horizontally, which is not the same as pulling it at 45. Do you see in each of those three directions, you're having a different effect on the object that you're trying to move? I mean, for instance, if I just did it vertically upwards, it wouldn't move up that hill. Wouldn't it just be picked off the ground? It wouldn't really move anywhere. Are we good? Right, next fella. Going to go back to 2D. Because there are 2D questions floating around. Oops, not on that page. Taking a few moments just to get this question set up. So what's this story going to be about? Let's make this decidedly different length there, right? At the origin, there are two vectors working on this point here. The vector u is pulling it at an angle of 30 degrees to the x-axis, right? And the vector v is pulling it at 30 degrees, but on the opposite side of the x-axis, going this way. Let's suppose we're also told that the magnitude of v is 10 newtons, and that the magnitude of v is only 8 newtons. What we can do with just the information that's in this picture and knowing this is that we can find the resultant force. We can find a single force that would be doing the same job of these two interacting with each other. So the kind of stories that very often go along with this are And these are two different tugboats, right? And at the origin, you've got your ship. If one of the tugboats was pushing it, pulling it this way, and the other tugboat was pulling it that way, what would be the net result? Well, the net result would probably be, you know, something along those lines there, right? And our job is to find that resultant force. So that's the kind of puzzle that we're now going to be looking at. How do you find what you get when you add these two vectors together, when all you're told is the magnitude of the vector and the angle it makes with the x-axis? Well, to do that, we incorporate a new formula, which you may have seen, or you should have seen in trig. Aye. And if you haven't seen that in trig, those people who've done vectors, you've seen that formula. It's called the x and the y component of a vector. You remember seeing those guys? I got a couple of notes. So that's the guy I'm going to be using. Let's see what that ends up giving us. Right, so let's do vector u first. Well, the magnitude of the vector u ends up being this fella times the cosine of 30 degrees, which ends up being 10 times the cosine of 30 degrees. I don't know why I'm making this so long. It doesn't need to be. Okay, we're looking at a cosine of 30. X coordinate, 30 degrees. It's a fraction. And it's not root 2 upon 2.
Root 3 over 2.
Yeah. Okay, that tidies up to being 5 root 3. Now, if you go the other way, then the y component is this fella. That's 10 times the sine of 30 degrees. And the sine of 30 degrees, I'll do that, is this fella. That means that the vector u is 5 root 3 and 5. We cool? Let's focus on the vector v now. Its x component is going to be the magnitude of v times the cosine of the angle. And its y is the magnitude of v times the sine of its angle. Well, we know the magnitude is 8 times the cosine of somebody. And then the other one is 8 times the sine of somebody. And here is a thing that you have to be aware of. In this picture, that angle there is 30 degrees. That is not the angle that gets written here in the cosine or here on the sine. The angle that we talk about when we talk about x and y components is described as the angle it makes with the positive x-axis. In other words, this line here. So we need to use that fella. So it's not 30 degrees. Are you all comfortable about why the second angle uses a 150 degree? Because we measure angles from the positive x-axis in an anti-clockwise rotation. And that angle is 30 short of 180, which is what 150 is. So that's now going to get me 8 times somebody and 8 times somebody else. Now, if you look at the cosine of 150, you'll find that it is virtually the same thing, but isn't it negative root 3 over 2? Sorry, positive root 3 upon 2. And the other fellow is, that's the negative, and this is the positive. If I had a brain, it'd be dangerous here. So negative 4 root 3 and 4. which kind of makes sense. It goes negative and then it goes up. So that makes the second vector negative 4 root 3 and 4. So the first stage in this process of trying to calculate what the resultant force is, which is this fella here, is that you have to find out what the vector u and v are in their component form. Now what do I do with these two vectors then to find this dotted line vector, the resultant force?
Can you move the paper up just a little bit, please?
Oh, I've got that issue, sorry. Wrong direction.
Okay, that's fine. Thank you.
Right. Okay, so back to my question. What do you do with the vectors u and v to get the vector that's the dotted line?
Subtract them.
Or
Add them.
add them. The key is almost in the name. Resultant, you know, the result. You add them together. So you add v, which in this case ends up being 5 root 3, 5, added to negative 4 root 3, 4. These two get you a root 3, and these two get you a 9. And now you have the resultant vector. So,
The top of the paper's cut off.
I'm not winning with this thing, am I? Oh, we did that yesterday. Can you see that line?
Today, you're
Yeah.
just a little angled on your setup.
Say again?
For today, it looks like you have the camera a little angled. That's the only difference.
Oh, okay. Now, can you see that line?
Yes.
No. Yes. Can you see that line?
Not the bottom line.
Yeah, I see that one.
Okay, so it's kind of yesterday. Keep away from the bottom. Leave it about half an inch. I got you. Okay, so what we have here is the answer to what do you get when you combine two vectors together when they're in this diagram form. Now, you could certainly turn it into decimals. What you could do to finish with, which I don't want to do, is, because it takes time, is let's suppose we call that answer the vector W. So the vector W is the resultant force. This would be the vector describing that dotted line. What you could also do then is, couldn't you find the magnitude of that vector? And couldn't you find the angle that that vector makes with the x-axis? And if you did that, you can do that quite easily, because the tangent of theta is the y component over the x, which in this case would be that fella. And the magnitude would be that guy squared plus that guy squared. So it'd be the square root of 84. So if you were being asked, if these two tugboats pulling the ship at the origin, what would be the resultant force? What would be the total length of it? The answer would be this number here. And what would the angle be, which is the angle it makes with the x-axis? Well, you know that the tangent of theta is the y-coordinate divided by the x-coordinate. So you could get theta by just finding whatever that guy is. I'm making this up. It's 13 degrees or something, right? It's not, but you can imagine what it would be. Any questions about the types of puzzles that we've done so far? Are we comfortable with those? Okay, then I shall move on. And this time, going to look at two vectors. And these two vectors are given in terms of some variable called t. And we're being told that these two vectors are perpendicular. So we're being told essentially that their dot product is 0. And the question is being find the value or values of t. So for what values of t will these two vectors be at 90 degrees to each other? Well, since you're told that they're at 90 degrees, you write down this. Now I'm going to do the dot product. So that guy times that guy is t squared, plus that guy times that guy is what, negative 2t, plus that guy times that guy is t lots of t plus 1, and the whole thing is going to equal 0. So that means t squared, take away 2t, plus a t squared plus a t equals 0. And in this case, oh, I could have made this a harder question. So t equals 0 is the only solution. Now what would that look like in the vector world? If you make t 0, you get 0, 0, 1. And if you make t equals 0, you get 0, negative 1, 0. And those two vectors are definitely at right angles to each other. You can imagine doing a dot product very quickly and you'd get 0. Yep. Let's move on to a fellow called a unit vector. Can you imagine, oh, actually, let me change his name. Let's call him V. Imagine I've got a vector V, just a general old three-dimensional vector. Two-dimensional vector would work as well. And it's called V. The unit vector is a vector parallel to it, we'll call that vector U, with one extra property. Its magnitude is 1. So the unit vector of any given vector is a vector that has the same direction, right, as the original vector V, but whose length is 1. Now, how do you calculate, or how do you find a unit vector? Well, let's suppose I give you a vector V, and it's equal to 3, negative 4, 12. And I'm being asked to find the unit vector for this vector. Well, first thing I'm going to do is find its magnitude, the magnitude of V. So it's 3 squared, negative 4 squared, add 12 squared, which is 9, add 16, add 144. Oh, 169. Got really lucky here. Its magnitude is 13. The unit vector, which we're going to call U, is 1 over the magnitude of V. Now, why does that generate a unit vector? Here goes. Do you know if you multiply the vector V by any scalar, and 1 over this fella is a scalar, right? It's a number. Don't you just get a vector that's parallel to it? So won't U be parallel to V because it's a multiple of V, right? 2 times V means I'm twice as long. A half times V means I'm half as long. But I'm still parallel to you in both situations. Now, if you take this vector and you multiply by 1 over its magnitude, won't you get a vector whose length is 1? Can you see why that formula works? I mean, if I stuck a big magnitude around this, the magnitude of this is that guy, which you can then split up, right? And you get 1. So all I do is find 1/13 of this vector, and I think I may have cut off the bottom, sorry. 3/13, -4/13, 12/13. So if you're being asked to find a unit vector, this is basically the process. Find the magnitude of the original vector, and then essentially divide its components by this number. So 3/13, -4/13, 12/13. So far, so good?
Professor, I had a question about that first
Yes.
one you did on
This
the
one here?
left.
Yes.
Yeah, wouldn't it be 2t²?
Did I do a screw up somewhere? Which one
Yeah,
would
so-
be 2t²?
So the,
Oh, here.
the third line.
Ah. Which is correct. So if I take t, what am I going to have? 2t take away 1?
Yeah.
So that means that t equals 0 still works. That's why I didn't realize I'd done a mistake. But isn't there another possibility that t is a
Yeah.
half as well? Which means
Okay.
then that if that's the first solution, let's see what the second solution is now that you fixed that for me. U is going to be using a half. So that'll be a half. 2 times a half will get you 1. And that'll get you 3 halves. And then if you plug a half in here, that guy will get you a half. This guy's -1. And this guy at the end is a half. And if this is correct, shouldn't these two vectors also have a dot product of 0 then? I'm pretty
Yeah.
sure they do, but let's just check it. A half times a half is a quarter. That guy's -1. That guy is 3/4. Isn't it nice when things come out exactly the way you want them to?
Yep.
Yeah. Now, a little issue with this fella here, and it's really just to get the answer in a format that you'll get the answer, you know, the software won't say you're wrong when you really are right. So I'm going to pick a very simple version of this question. Suppose I have a vector 1, 1, 1, and I want to find the unit vector. The magnitude of that vector, can you just trust me, it's square root of 3. So the unit vector ends up being 1 over root 3, 1 over root 3, 1 over root 3. Okay, original vector divided by this fella. Everything looks fine. Whoops. Isn't that equivalent? Isn't 1 over root 3 the same thing as root 3 over 3? So when you're looking at some of your answers, and I think a member of your class sent me an issue with this, the textbook is typically looking for exact values unless it says give the answer to the nearest whole number or to 1 decimal place. And when it's asking for exact values, it can sometimes be nitpicky about it. So if you had an answer that was that, you would rationalize the denominator and simplify. So this is that, but this is considered better form than that. If your answer is the square root of 40, you know that's the square root of 4 times 10. That is 2 root 10. This is the same value as that, but this is considered better form. So you may be doing it right. What I'm just saying is be careful because the software isn't very friendly sometimes. In fact, I think it's not even consistent. Like you might do question 2 and the square root of 40 goes fine. And then you do question 3 and it doesn't like it. It wants 2 root 10 for no particular rhyme or reason. So it's one of those things that it just does because it does, right? Has anyone came across that issue that you had to write the answer in a particular version rather than just maybe the one that you had in front of you?
No, they
Okay.
all seem to plug in fine for me.
Right. So they'll take a square root of 40 and they'll take a 2's root 10. What I don't think they'll take is 8.1234 because that is just a decimal version of it, right? Pretty sure they won't take that. I think I've just got, on the top of my head anyway, I just got one more thing, and then we'll spend a few minutes looking at the homework and scanning through it in case there's a particular question that I may not have covered. And then we'll call dot product done, and then we'll start the next one, which is vector cross products. So here's my last guy. Let me start by saying this picture is going to look decidedly ugly, but I don't know how to draw it nicely. I want you to imagine a vector where you start at the origin. You don't need to for vectors typically, but this one is a good idea to start at the origin. And this vector, I'm calling it V, is this guy here. And I want you to imagine that vector V is actually sticking out of the paper like this pen, right? So this is a two-dimensional version of what's really a three-dimensional thing. And we're going to look at things called direction cosines. Direction cosines. Now, this vector makes an angle with the x-axis, the positive x-axis, it makes an angle with the positive y-axis, and it makes an angle with the positive z-axis. The angle that it makes with the x-axis is called alpha. The angle that it makes with the y-axis, can I find a blue pen here? It's called beta. Excuse me. There we go. Called beta. Sorry. With y-axis is called beta. And the angle that it makes with the z-axis is called gamma. Right, and would you agree my picture's pretty ugly, right? There's a lot going on here. So you just got, it's just, you can't do it. It's 3D and you're trying to do it in 2D. But essentially, these are called the direction cosines. Now, the word cosine is important because essentially what it tells us is that if you have a unit vector, and the unit vector is called u1, u2, u3, then the vector u is going to be the cosine of alpha, the cosine of beta, and the cosine of gamma. In other words, the cosine of that angle is the x component of the unit vector. The cosine of beta is the y coordinate or the y component, and the cosine of gamma is that fella. These are called direction cosines. So if someone say again?
Oh, never mind. Go on.
Right. So what we're looking at here is that there is a direct connection between a unit vector and the angles that that unit vector make with the x, y, and z axis. Right. So let's suppose that I have a vector v, and it's 1, 2, -3. Now the magnitude of v is going to be 9, 10. You can just trust me, it's the square root of 14. But you can double check as I'm doing it. So won't the unit vector be 1 over root 14, 2 over root 14, comma -3 over root 14? So this is the unit vector of v. I can now use these three values to find the missing size of angle alpha, angle beta, and angle gamma. For example, the cosine of alpha is that fella, which means then that alpha is the inverse cosine of this guy. Let's see if I can do that. Inverse cosine of 1 divided by the square root of 14. And it's about 74.5 degrees, roughly. So if you wanted to know what size the vector v makes with the x-axis, what you have to do first is find the unit vector for v. Then these numbers here will tell you what the cosine of alpha is, the cosine of beta is this fellow, and the cosine of gamma is that one. Now, if I tell you that alpha is 74.5 degrees, which it is, and I go and I find beta and gamma, and I'll just do them quickly. So the inverse cosine of that guy, see what that looks like. The inverse cosine of 2 divided by the square root, inverse cosine of 2 divided by the square root 14. That guy there is roughly 57.7 degrees. And if you go for gamma, then what do you know about that fella? He's the inverse cosine of this. So one last inverse cosine to do. And the inverse cosine of -3 divided by the square root of 14. And I'm looking at 143.3 degrees. Now you may have thought that those three angles might add up to, I don't know, 180 or 360 or some nice number like that. And if you look at them really carefully, do you know that they don't add up to anything particular? And that's the case. The angles that a vector makes with the x, y, and z axes do not add up to any specific total, right? In some vectors, they add up to 22 degrees. In other situations, they end up being 222 degrees. So there is no direct connection, at least in the addition, but there is one connection that is true. Oops. The squares of the cosines, not the angles themselves, but the cosines themselves. Do you know what the squares of the three cosines add up to? They always add up to the same number.
Is it 1?
Yes. Because isn't that guy squared plus that guy squared plus that guy squared the same thing as the square root of its magnitude? And the square root of 1 is still 1, so it ends up being 1. That tells me, do you know if I know alpha and beta, can't I find gamma? Suppose I tell you that alpha was root 2 over 2. And I told you beta was, say, 1/2. I should be able to find gamma, or at least two choices for it, by not doing nothing but using this. Right, if this is the angle, right, the cosine of if the cosine of alpha is this and the cosine of beta is that, then I should be able to square this guy, which is what, 2 over 4, and 1 over 4, plus this guy. So I have 3/4, which means cos squared gamma is 1/4, which means the cosine of gamma is either plus or minus 1/2. And then I could actually find out what angle gamma is. So these are called direction cosines. Essentially what it says is that the components of a unit vector are the same as the cosine of the angles it makes with the x, the y, and the z axes in 3D. Any questions about that before we have a look at the homework?
Mr. Robertson, why we
Yes.
use direction cosines and not direction sines or direction tangents? Could you explain that using like a diagram? Thank you.
I wish I could, but I can't. The relationship is built using the cosines. The math behind it is quite messy. Basically, it involves projections of this vector onto the xy plane, the zy plane, and finally the zx plane. And when you do those projections, the cosine gives a nice relationship. If you try to do the same relationship in terms of sine, you could do it, but it wouldn't be as pretty. To give you an example, if I know that the cosine of alpha is just u1, which it is, then won't cosine squared of alpha be u1 squared? And won't 1 take away cosine alpha be 1 take away u1 squared? And isn't that the same thing as sine squared alpha? Which means the sine of alpha would be the square root of 1 take away u1 squared. You see, it's not very pretty when you do the angles in terms of the sine relationship. And if you try to do the angles in terms of the tangent, you would have to do this guy. See, in this case here, cosine of alpha is just equal to u1. In this case, the sine of alpha is that ugly guy. And if I try to, do you know the tan of alpha? It would be the sine of alpha would be over the cosine of alpha. And these two versions are not very elegant, whereas this one is really cool. Now, proving that is much more difficult to do. I'm sure if you went online, you could probably see the proof of it. It wouldn't surprise me if it was a couple of pages long, and certainly messy. So that's why they use, it's called the cosines, right? Direction cosines, and not called the direction sines, because that formula is messy, and definitely not called the direction tangents, which is even uglier. Right, let's have a look at our homework. That's right. Oh, I've got some chat here. See if there's some questions here. Okay. And someone's got a video. That's cool.
I just linked the video for the proof of the cosine direction.
Oh, the cosine. Well done. I didn't know that. I might click on that. I've got too many things, but that is cool. I wish I had more time. Let's go and check out some homework questions. I believe this is set up. I just want to scan through these and see if I've covered all bases. I know I haven't covered this one, but I was pretty sure I was going to do it right now. Let's take these solutions out. They're a big distraction to me. Okay, here goes. It says, which of the following expressions are meaningful and which are meaningless? Right. If you're doing a dot product, don't you have to have a vector dot product vector? You can't go the number 5 dot product, the vector 1, 2, 3, right? It is meaningless. So dot products, you need 2 vectors. Right? So let's see what we can get. If you were doing this one, A dot B would get me a scalar, and then you'd have a scalar dot product a vector. So that's meaningless. What about A dot B, right? You can do A dot B, right? That's 2 vectors. And won't you get a scalar, like 4? Isn't 4C allowed? It's just a multiple of the vector C. So A is meaningless, B you can do. Right, what about C? Is the magnitude of A vector or a scalar? Is the magnitude of A number or a vector, essentially?
That's a number.
Okay. Is B dot C a vector or a scalar?
That should be a vector.
Is B dot C a vector? Isn't it the dot product of 2 vectors?
Oh,
And
so
what does
yeah, it would just be a number then.
Just be a number, right? the correct term's scalar, but number's a good word to use in your head because you can think of numbers better than scalars. Scalars are a little bit abstract sounding. So what you're essentially getting here is a number times another number, which means it's valid, right? You could do it. How about D then? A dot B add C, right? Since it's in the brackets, we should do B add C. If you add two vectors together, don't you get a vector? And then isn't A dot a vector? Okay, you can do that. So it has a meaning. Let's look at E. A dot B, you can do A dot B and you get a scalar, right? You get a number. Can you take a number and add a vector to it? Can you go 5 plus the vector 1, 2, 3? No, so that is meaningless. What about F, the last one? The magnitude of A is a scalar. And a scalar with a dot product never works, right? You can't do 5 dot product 1, 2, 3, right? You need a dot product needs a vector, dot, a second vector. So that's what that was about. Just find A dot B, they're pretty straightforward, don't see any issues with that. Okay, let's look at this fella. It's another one of the puzzles. Can you see it's another equilateral triangle? The vectors are guaranteed to be the same length, but it's easy to miss. They're the same length, and isn't the length 1? Because they're unit vectors. Now, if you were doing U dot V, so here is U, here is V. If you wanted to find the dot product of U dot V, you would be doing the magnitude of U times the magnitude of V times the cosine of the angle between them. Well, won't that be 1 times the cosine of 60? So you might think that U dot W is going to be the same answer, but it's not. This is a vector U, this is a vector W. If you're doing the dot product U dot W, see this vector here? It really belongs down here. Do you see that the angle you're going to make for the second one is 120 degrees? The vector U and the vector V. So if you rub out this fella here, pretend he's not there, and you drop this vector down so that they start at the same point and they leave from the same point, I should say, right? Do you see that the angle is now not the 60, but if you continue it, it's 120. Find angles of vectors. Okay, suppose I was doing question 29. Are these vectors, are they right angled? See this guy here? P, Q, and R. Now I could do this two different ways. I could do it using dot products. I could do it using just magnitudes of vectors. But won't you first have to find P, Q, and PR? And then you can use the dot product. And if it's 0, you say yes, it's right angled. And if the dot product of PQ with PR is not the number 0, then it's not right angled. You see, that's much quicker than finding all 3 lengths and then using the inverse of Pythagoras. There's a direction cosine question for you. Here's another direction cosine question for you. Here's one where you're told 2 and you're being asked to find gamma, third one. Here's a, oh yeah, there's the pull the thing up the hill question. Right, there's the force vector from P to Q. I'd call this P, probably I'd call this Q. So you're going to find the dot product of F with the vector joining P to Q, and that will be your answer. 14 is basically, here's a formula, plug in A, B, and C and see what you get. Oh, that one I haven't done. Find the angle between the diagonal of a cube and one of its edges. Well, I'm going to do that one, or at least start it for you. But let's just finish this off. Dot product. You know how you do the dot product? Length of magnitude of A, magnitude of B, cosine of 45. Pretty standard questions. Some more dot products, guys. Oh, there's that version of the question I did with the t's and screwed up a little bit. And classic, find the angle between two vectors. And the last ones, they give you plenty of videos to watch. Right, I scanned through them pretty quickly, with the exception of the one that I'm going to do in a few moments, the one to do with the angle one of its diagonals makes with the edges, which was, what's the question? Is there any other questions from that that you are not sure about that you'd like me to talk about? Okay, then let's get started on that cube story. What they gave us is not an awful lot of information. They said, look, you've got a cube in 3D space. So here goes. That's pretty good for me. A cube in 3D space. And we want to find the angle that one of its diagonals makes with one of its sides. So evidently, it doesn't matter which one you pick because they must all be the same for some reason. So I'm going to try and pick one to do. So can you imagine this vector here? Maybe make a new color. So this here is one of the guys, right? Actually, is that one of the diagonals? Well, strictly speaking, it's not, so I'll have to pick another one. It's one of the problems of doing, there we go. This is one of the diagonals, and I'm going to make this guy meet up with this guy. So this blue line is going to be one of our vectors. This here is going to be one of the edges that they're talking about, and I'm trying to find this angle between them. So if I redraw my picture, but just focus on the vector that goes like that, meeting up with a vector that goes like that, and this is the angle that I'm trying to get. I'm going to add a little invisible dotted line going this way as well. So how am I going to find the size of that angle when all I know is it's a cube and this line here is going to be the diagonal? Well, I could do that a couple of ways. First way I'm going to do it is using dot products. I think that's the easiest way. Now, if I look at this point here and this point here, right? So that would be, I'll call this P and I'll call this Q. If I can find the vector PQ, right? And this guy's Q, and I'm going to call this guy down here R, and I can find the vector QR, PQ and QR. Actually, let me redo that. Let's do QP and QR, that's better. I'll go this way. Then I should be able to find the size of the angle between them. So what do I know about the coordinates of P, the coordinates of Q, and finally the coordinates of R? Well, since this is a cube, oh, here's a little cheat. I think it works. They didn't mention the cube. Doesn't that mean then that it doesn't matter how big or small the cube is, the angle that we're trying to find called theta is going to be the same number every single time? So because of that, I'm going to make the assumption that the cube is 1 units in every direction. So if you want to get this fella here, P, he's going to be 1 in the X, right? 1 in the X, 0 in the Y, and 0 in the Z. Now I want to get Q. Q is here. Now what does Q look like? 0 in the X, 1 in the Y, 1 in the R, Z. Now R is this guy down here. And R is 0 in the X, 1 in the Y, and 0 in the R. So what I've done is I've found the coordinates of P, Q, and R. P, Q, and R. So the vector QP, and the reason I decided to change my orientation is if you want to find the angle theta, don't you have to leave Q in both directions? So you have to go QP and QR to find the angle between those two. So QP ends up being 1 take away 0, 0 take away 1, 0 take away 1. And QR is 0 take away 0, 1 take away 0, or 1 take away 1, 0, and 0 take away 1, which is that. And that's as far as I want to go on that question. If you know those two vectors, can't you find the angle between them the usual way? It's not difficult. Would you agree the dot product is 1? And the magnitude of the QP is what, √3, and the magnitude of QR is that guy. So it looks like the cosine of the angle is going to be 1 over √3, which is about 55 degrees, I think it is. And that is the end of dot products as far as we're concerned. Your last chance, is there anything in dot products that you want me to go over before we move on to our new guy, which is going to be cross products? Are we good? Okay. Oh, now we're going to get really visual. Suppose I have two vectors called u and v in 3 dimensions. Can we pretend it's these two vectors here, right? There is a calculation called the cross product, which is written as u cross v. And it's a big letter X, and you read it out loud as u cross v. We call this the cross product of u and v. What this generates, this thing here, it generates a vector. Oh, let's call it W. That has the property that it is orthogonal, right angled, to both u and v. So if you have two vectors, one called u and the other called v, the cross product will give you a third vector that is orthogonal to both of those. So can you imagine that this was the vector u and this was the vector v? Then the cross product would be a vector that would look something like this. And it has the property that it makes a right angle with both those vectors. That cross product is quite complicated to calculate. It's numerically messy, but it is doable. And there's a formula for it, which I will not show you because it's atrociously ugly. What I'll show you instead is what typically everybody I know at least does it, and they do it geometrically, right? There's a way to do this answer geometrically. Now you might think, apart from just the mathematical interest of it, why you would want to find a vector that's orthogonal to two other vectors. There's some really quite interesting applications to the cross product. For instance, one of them, do you know if you have a if you want to calculate the torque, which some of you probably know what that is, trucks have torque. But you know, if you take a wrench and a bolt and you give it a turn, that you're generating torque as well, right? the direction of that torque, right, is the cross product of the angle in which you're turning your wrench and the direction in which the bolt is pointing. So you can actually use it to calculate all sorts of cool things. If you're an engineer, at least, you can. So how do we calculate this guy? And I said he's messy, and he is. And before I even show you that, I have to show you something first. Hopefully you've seen matrices before. This is what's called a 2x2 matrix. It's a square matrix, 2 rows, 2 columns. I guess I should put a negative number in there, right? And it's made up of 4 numbers, essentially. If you put a vertical line around them, yes, the same vertical line that we use for absolute value and magnitude, that symbol seems to be getting plenty of usage, right? If you see this written down, you're finding what's called the determinant of a matrix. Has anyone seen that process of how to find the determinant of a 2x2 matrix? Okay. So let's show you how you do it then. These 2 numbers here are called the major diagonal. You multiply those 2 together. Then you take away the other 2, and these are called the minor diagonal. So you'll hear me say major take away minor, that's what I'm talking about. These 2 numbers are the major, these 2 numbers make up the minor. So you go 2 times 4, take away 5 times -3, which gives you 8, take away -15. In this case, 8, add 15. So the determinant would be 23. Are you comfortable about how to find this thing called the determinant of a 2x2 matrix? Major, take away minor. It's kind of cross motion. Okay. Now, if you take our 2 vectors that we had originally, I can't see if I can find them again. If not, I'll just make up another 2. Oh, they're under here. How do we find this new guy called the cross product, right? So we're going to use these 2 fellas. U is the matrix, is the vector 1, 2, 3. And V is the vector 5, 6, -1. Okay. To get the cross product, you set up a 3x3 matrix. And the vector U is first, so that goes 1, 2, 3. And the vector V is second, that goes 5, 6, -1. So this is a 3x3 matrix. The first row has the vectors I, j, k, you know, the unit vectors for x, y, and z. The second row has the components of vector U, and the third row has the components of vector V. So you set this fella up. And then you do, this is the last part of the messy bit. You find what is called the determinant of this matrix, and it's made up of something I, take away some number j, plus some number k. So the component I, take away something j, add something k. So how do we find the numbers that go here, here, and here? Because that's the guys that we are waiting for. Okay. Well, let's show you. To get I, it's very visual, this. Oops, pen's been awkward. You cover up column I. Do you see a little 2x2 matrix there? See it? Cover up I. So you go major diagonal, -2, take away minor diagonal 18. So -2 take away 18, and -2 take away, so I'll show you, -2 take away 18 is -20. Now you want to get the middle one, major diagonal -1, subtract 15, that's -16. And lastly, to get the K one, you cover up column K, major diagonal 6, take away minor diagonal 10. 6 take away 10 is -4. And then we just tidy it up. -20, a negative of a negative, and finally the third fella. And there you have found your first cross product. This vector here, -20, 16, -4, is orthogonal to the vector u. It's also at the same time going to be orthogonal to the vector v. I wouldn't normally do this because it takes up a lot of time, but let's check it out. Let's find out if this guy truly is orthogonal to that guy. It isn't the quick way of doing that is just to take dot product, right? And if the dot product is 0, it means it's orthogonal. So if I take the vector 1, 2, 3, and I do a dot product with this fella. Oh, by the way, if this doesn't work, it's because I can't count. 1 times -20. Add 2 times 16. Add 3 times -4. So that's -20 plus 32, take away 12. Am I good or am I good? So I didn't screw up. In fact, if that was a test, couldn't you do that as a quick check that you didn't screw up yourself? So we now have a very artificial mechanical process that allows us to find the cross product of any two vectors. We now know how to find a third vector that's orthogonal to two given vectors. And right now, that's all we're going to be focusing on getting practice at. So I'm going to do one more of these guys from kind of start to finish. And hopefully that will work. Any questions for this double page disappears? Okay, watch. I'll do this last one a little bit slower. Right, just to prove to you that this technique works, randomly give me 3 digits for you. I'll write them down, just so, just chuck in some numbers for me.
312.
That'll work. Okay, let's do V and at least chuck one negative in amongst it as well, just to, you know, keep the thing going.
-483.
Right, so would you all agree that are totally random vectors? Now, if we didn't have this mechanical way of calculating the cross product, can you imagine how difficult it would be to find a vector orthogonal to 2 vectors at the same time? I mean, the process, you could guess, I guess, but that wouldn't really be very successful. So, cross product. You set up every single time the same way. IJK is your first row. You put in U, and then you put in V. And then it's going to be so many I's, take away so many J's, plus so many K's. Notice it's easy to miss that until you've done a few of them. Have you noticed that the middle one always has an extra negative involved in it? The other two are just the way they are, but the middle one, the J term, has an extra negative involved. Right, so cover that guy up. That's going to get me the I component. Major is 3, take away minor, which is 16, negative 13. Middle one. The major is 9, take away negative 8 is like adding 8, so you get 17. Major is 24, take away negative 4, 24 take away 4 is add 4, 28. That gets me the answer negative 13, negative 17, and 28. As a process goes, does that seem kind of mechanical? You know, I'm doing the same thing every time. All that's changing is the numbers I'm doing it to, right? It's always ijk. This is always u. This one is the second vector v. Cover it up. Do the thing. Cross major, minor. Major, take away minor. Any ideas what that might do? Suppose I switched the U position and the V position. What do you think the new cross product might look like?
Isn't it gonna be, because if you think about it, wouldn't it just be perpendicular in the opposite 180 direction of the first cross?
Yes, it will be, exactly. Which I could write, I guess, mathematically as that. Do you know that funny, there's my hand, you know that x-axis, y-axis, z-axis is called the right-hand rule, right? If you switch the order of things, this hurts like heck, but your thumb points down the way when you reverse the x and y positions, right? If you make one, the other finger the U and the other finger the V. So if you think this is U, this is V, my thumb is the cross product. But if you switch places with them, you end up pointing down the way. And so that's really what you would get. What do you think you would get if the cross product, if U and V were parallel to each other? Suppose U and V weren't totally independent, you know, like this, but were basically that. What do you think the cross product would be equal to in a situation where that was true?
Would it be a multiple of one of them?
That's a possibility. It's even stranger than that. It's the zero vector. So do you know someone says, here are two vectors, and prove to me that one of them is, you know, parallel to the other. A long-winded way of doing it would be just to find the cross product and getting zero as your answer. Provided neither of the two vectors is a zero vector. If a cross product is zero, it means that they're parallel to each other. Actually, if someone went and said to me, prove that two vectors are parallel or not, do you know, I would just divide the x's, the y's, and the z's and see if there were multiples, which is much quicker. So there are lots of different properties. Do you know if you take the cross product of U and V and you find the magnitude of it, right? So basically, if I found the magnitude of this fellow, do you know that you actually get something geometric? And it's totally not intuitive to me. If you imagine this is the vector U in 3D, and this is the vector V in 3D, the cross product would be probably sticking out the paper, something like this, right? The magnitude of that vector is equal to the area of the parallelogram. Now that is totally not, it's hard to imagine why that should be true, why the magnitude of a cross product should be equal to the area of the parallelogram that's formed by using U and V. And this is a parallelogram floating in 3D space. It's not flat on the floor, it's actually at an angle. That's amazing. Do you know that 1/2 this magnitude is the area of the triangle. And what triangle am I talking about? I'm talking about this triangle here. So if you know two vectors u and v, and you want to know what the area of the triangle that's formed by u and v, and then just join the two endpoints together, the area of that triangle is a half of the magnitude of its cross product. I think that's kind of cool. And there's all sorts of, next time we'll find out about a shape called a parallelepiped, which is really a three-dimensional parallelogram, and the cross product is involved in that as well. Well, that is going to be us for today.